A primary key is like a person's passport number. It is a set of one or more columns that tells us exactly which row we are looking at, and no two rows can have the same passport number. Formally, if we have a table R that contains tuples T1 and T2, and K is the set of columns chosen as the primary key, then the projection of T1 on K equals the projection of T2 on K implies T1 equals T2. Pi sub k denotes the projection on the columns in K. This means that equal values on the key columns force the whole rows to be identical. In addition, a primary key may never contain null, because a missing value would break the unique, identifies the row rule. Example, a table called student with columns student ID, name, and birth date where student ID is the primary key. Every student has a different student ID and none can be null. When we pick a primary key, we want the smallest set of columns that still makes every row unique. That is the minimality idea. Imagine you have a library book record with ISBN, title, author, publication year. ISBN alone is enough to point to one book, so we choose it. If we tried to use ISBN title, we would still be unique, but we added an unnecessary column. Minimality says remove any column from the key, and you would lose the uniqueness property. This also gives us the notion of a candidate key, any minimal set that uniquely identifies a row. So we prefer the shortest, easiest to type key, which reduces storage and makes joins faster. In set theoretic terms, a table R is a subset of the Cartesian product of its attribute domains. R is a subset of D1 cross D2 cross Dn. A primary key K equals the set of 1 through a K defines a function f from the set of key values to the set of rows. F colon pi sub k of R maps to R, where pi sub k of R is the projection of R on K. The function f must be injective. Different key values map to different rows. Formally, for all x, y and pi sub k of R, f of x equals f of y implies x equals y. The injective property guarantees the uniqueness rule, while the total property, every row has a key value, guarantees that no key column can be null. This mathematical view helps us reason about constraints independent of any particular DBMS. A foreign key is like a reference in a story that points back to a character's name mentioned earlier. Technically, a foreign key is a set of columns in a child table whose values must either be null or must exactly match values of the primary or unique key in a parent table. For example, an orders table may have a column customer ID that is a foreign key referencing the customer ID primary key of the customer's table. This creates a link. Every order must belong to an existing customer, preventing orphan orders that refer to nobody. Referential integrity is the rule that the linked values stay consistent when the parent data changes. DBMSs let us tell the system what to do when a referenced primary key row is updated or deleted. On update cascade, if a parent's key changes, the DB automatically changes all matching foreign keys, like updating a family surname in all members' records. On delete cascade, deleting a parent row also deletes all child rows, like removing a teacher and automatically dropping all their class schedules. On delete set null, the foreign key in child rows is set to null instead of being deleted like a book, losing its author info when the author leaves the system. These rules keep the database from ending up with broken references. Entity relationship (ER) diagrams use lines to show how entities relate, and those lines turn into primary key foreign key patterns in tables. A 1-to-1, 1:1 relationship puts the primary key of one table as a foreign key in the other or merges them. A 1-to-many, 1:n relationship places the primary key of the one side as a foreign key in the many side. For example, one customer has many orders, so orders.customer ID is a foreign key. A many-to-many, m:(n) relationship needs a bridge junction table that contains two foreign keys, each referencing the primary key of the participating tables. The pair of foreign keys together often form the bridge's primary key, for example, students-courses enrollment table. This mapping preserves the cardinalities shown in the ER diagram. Primary and foreign keys are the backbone of the normal forms. In first normal form, 1NF, we already have atomic columns, but a primary key guarantees each row is uniquely identifiable. Second normal form, 2NF, eliminates partial dependency on a composite key. If a non-key attribute depends only on part of a composite primary key, we split the table and use a foreign key to reconnect. Third normal form, 3NF, and BCNF require that every non-key attribute be fully dependent on the whole primary key and not on anything else. Foreign keys help preserve these dependencies after decomposition because they relink the smaller tables together. Thus, when we decompose a big table into smaller ones, we keep foreign keys to ensure we can join the pieces back without losing information. Most databases automatically create an index on the primary key columns. Think of an index as a sorted phone book that lets the DB find a row without scanning the whole table. The index is usually a Bay tree, which gives O of log n lookup time. Foreign keys are not always indexed automatically, but adding an index on a foreign key speeds up joins and cascade operations. The trade-off is extra storage. Each index entry stores the key value plus a pointer to the data row, so a large table with many indexes can consume significant disk space. However, the performance gain for queries, updates, and referential integrity checks usually outweighs the overhead. Explanation: different RDBMS enforce constraints in slightly different ways, but the idea is the same. MySQL stores primary key and foreign key definitions in its InnoDB engine. It checks the constraints during insert, update, and delete, and raises an error if a rule is violated. PostgreSQL uses system catalogs to track constraints and performs the checks as part of each statement's execution plan. It also supports deferred constraint checking at transaction commit. Oracle implements constraints as part of the data dictionary and validates them on each DML operation. It provides rich options for on-delete or update actions and can use triggers for custom logic. SQL Server keeps constraint metadata in system tables and automatically creates a unique index for primary keys. Foreign key checks are performed row by row, and you can also define cascading actions. All these platforms may use internal triggers or hidden system code to enforce the rules, and they expose the same SQL syntax, primary key, foreign key, references on delete, so developers can write portable definitions.